Hello and welcome TYBSc physics friends. In the series of these video lectures on multiple choice questions on the subject atomic and molecular spectra, we have already discussed three chapters, chapter 1, 2 and 3. This is the chapter number 4 from our syllabus. That title of the chapter is Zeeman Effect. We will discuss a few multiple choice questions on this chapter 2. Note that this chapter consists of two separate parts. One is called as Zeeman Effect and second is the Stark Effect. We have tried to take or design as much as simple multiple choice questions which may be asked in the forthcoming SPPU semester examination. All this I'm very thankful to my colleague Dr. Smita Lokre, who has designed all these questions for all of you. I'm discussing these questions one by one as follows. Now, first question. In normal Zeeman effect, the single spectral line splits up into dash number of components. 4 options are given, only 1, 2, option C is 3 and option D is several. Now this is the normal Zeeman effect. So you might have seen earlier when there is no magnetic field applied, so H or B, if this magnetic applied is simply 0, no magnetic field, in general we observe only one line, spectral line in the radiation spectrum or spectrum of an atom. But when certain field is applied, if it is not equal to 0, then this particular type of spectral lines get splitted in such a manner. There is one original line and there are two lines, one on the left hand side and one is on the right hand side. So with some less frequency and another line with some higher frequency and with the original frequency, or you can talk in terms of wavelength too. So such type of splitting is observed and this is called as normal Zeeman effect. So usually a singlet or single line gets splitted in 3 different lines, or that becomes a triplet, and that effect is called as the normal Zeeman effect. Therefore, correct option of this question number 1 is C, that is 3. So once again, in normal Zeeman effect, the single spectral line splits into 3 components, and therefore correct option of question number 1 is C. Now on the other hand, in second, that is the in anomalous Zeeman effect, the single spectral line splits up into number of components. Earlier we have seen if there is no magnetic field, then only one, there is no question of splitting, or there is no question of Zeeman effect. 2 lines are again not possible. 3 lines, when we have seen, it is a normal Zeeman effect, and therefore a particular single line, again here we can go here, this is for an effect H is 0, and when this H is non-zero but this is weak, when the applied magnetic field is weak, in earlier case it is strong, in that case these spectral lines are found to be splitted in number of lines, usually 4 to 6 and so on, and this effect is called as the anomalous Zeeman effect, and therefore this not even 4 and 6 but several number of lines can be observed, and therefore question number 2 correct answer is D, several components. Now question number 3, the effect Zeeman effect is observed when the atoms are placed in option A, magnetic field, option B, electric field, option C is electromagnetic field, and option D is the none of the above. So this is a straight away definition of the Zeeman effect. Whenever a source of radiation or the spectrum from which we are getting, if it is kept in certain magnetic field, if the source of radiation, and if I apply this is N pole and this is N pole or some electromagnet, in this case if I go for observing the spectral lines from that radiation, there are 2 views. This is called as transverse view, and there is another view here from this direction, this is called as longitudinal view. So depending upon that, you find this particular spectral lines get splitted, so singlet gets triplet gets multiple lines, and these are possible, and this effect is called as Zeeman effect, and this is possible when a strong electromagnetic field is applied over this particular source of radiation, and that's what correct answer of this question number 3 is A, that is magnetic field. Whereas question number 4 is a different one. The Stark effect is observed when the atoms, same case again. So in spite of this, if I apply, this is an electric field, some positive charges or this, and there are negative charges here. This is negative charge plate, and in this case there is a electric field as we show here from positive to negative. And when this source of radiation is kept here and observe the spectral lines from this using the telescope, and you will find this type of effect here also. This electric field changes or splits the spectral lines, and this particular splitting or this effect is called as Stark effect. So naturally or basically this Stark effect is observed when the atoms are placed in the electric field. So if it is in magnetic, then it is Zeeman effect. If it is in electric field, then it is the Stark effect. So Zeeman effect and Stark effect are one of the very prominent effects, and you might be knowing that Stark effect was well discovered in 1896 somewhere. This Zeeman effect was introduced around 1896, and in 1913 almost 20 or that much years, 17 years required to come for this Stark effect, because I think you might be knowing this keeping this or producing this type of strong electric field in which such type of the radiating material is to be kept, that was a big difficulty, and that was resolved by Stark. And that's what after long period, this Stark effect was introduced later on after Zeeman effect. So this is all interesting things one can go for understanding of all these things. Question number 5. The normal Zeeman effect consists of triplet when viewed in dash dash direction and a doublet when viewed in the dash dash direction. Now as we have already drawn this diagram, usually this is what a diagram you might have drawn earlier. There is a Bohr or the hole inside this particular magnetic pole. So like this I can draw here. This is N pole and this is the S pole, wherein this type of small Bohr is kept there, and this becomes an S pole. So this is magnetic field, and now the source of radiation is kept here. So this is the source of radiation, and you have to observe this through telescope in these two different directions. So this is still telescope here, and same telescope also can be put here. This is another telescope. So this is how you can observe this radiation this way, or this you can observe this radiation this way. Here this is the direction of the magnetic field, B or H you can take, and when we are waving in the direction parallel to the direction of the magnetic field through this telescope, usually these are found to be the two lines. So it is found to be a doublet. One of the line is absent, so this in between line is absent, and one left hand side and right hand side is only observed, and this is found to be a doublet. So when this this particular telescope is kept in the direction parallel to the or anti-parallel to the direction of magnetic field, in the spectrum these two lines are observed, and they are supposed to have this orientation, or their polarization is found to be circularly polarized in the opposite direction, and in between line is missing, and that type of line is not observed, and this is called as a doublet. Whereas if it is looked through this particular transverse direction or perpendicular direction to the direction of magnetic field, in this case these three lines are observed as usual in the Zeeman effect. So this is how triplet is observed when we look in the transverse direction, and doublet is observed when we look in the when we observe or analyze the spectrum in the longitudinal direction or in the parallel direction. That's why this option B is the correct option of this question number 5. So many a times these words may be changed. So transverse view, in spite of that we will call perpendicular view. Longitudinal view, in spite of we may call as a parallel view, or in the direction of the field, or in the direction perpendicular to the direction of the magnetic field. So lot many words can be changed, but the situation remains same, that in the transverse view there are three lines observed, and in the longitudinal view there are two lines observed in case of the normal Zeeman effect. That is what the question number 5. Question number 6. Normal Zeeman effect is obtained from the elements like. Now this is again a theoretical question. Here the normal Zeeman effect is observed when this particular type of singlets gets splitted in the triplets, or the three different energy levels are one single energy levels gets splitted, and this phenomenon is observed usually for the elements which are having their orbital angular momentum to be spin angular momentum and orbital angular momentum, as we all know, is in that case this s to be equal to 0. S to be equal to 0. In that case, this multiplicity is twice plus 1. So multiplicity is simply equal to 1. So all such elements which are having this type of possibility, these are calcium, copper, zinc and cadmium. So these another pairs Na and Cr, these are elements which are having single unpaired electron, and therefore their spin angular momentum behaves in a different manner, and that's why its effect is something different than this normal Zeeman effect. So when the electrons are paired and the total angular momentum, spin angular momentum of the system is found to be 0, then in that case this type of normal Zeeman effect is observed. And all these examples, Cap, copper, calcium, zinc and Cd, this is the proper pair here, or the elements which show a normal Zeeman effect in this case. Whereas this Na, sodium, chromium etc., these are the having elements having unpaired electron and thereby having some angular spin angular momentum, and therefore these elements show another effect that is called as anomalous Zeeman effect. So anomalous Zeeman effect is, that is question number 7. Anomalous Zeeman effect is obtained from the element like, straight away this is sodium and chromium, because they possess unpaired electron like this 3s1, and this 3s1 electron, this 3s electron has L value is equal to 0, whereas S value is equal to 1/2. Therefore capital S is also equal to 1/2, and this time multiplicity is bit different than what we have seen earlier, and therefore this type of elements gives rise to a effect, or that is called as anomalous Zeeman effect. And therefore correct answer of this question number 7 is B, sodium and chromium. Then question number 8, at higher magnetic field the splitting of spectral lines is disturbed, and this effect is called as, again, no Stark effect. It is not a Stark effect, it is not a normal Zeeman effect, because that ordinary magnetic fields are applied and such type of effect is observed there. Whereas in a higher magnetic field, this anomalous Zeeman effect can be seen. Actually anomalous Zeeman effect is observed when this H, or the magnetic field applied, is small one, weak magnetic field. So naturally answer of this question is B, it is called as normal Zeeman effect. So higher magnetic fields, the splitting of the spectral lines is disturbed, and this effect is, actually there is one more effect is called as Paschen-Back effect, okay, and this is not given in option, but you can check whether this option, any of this option is correct or not. So this, at very high magnetic field, this particular type of multiple splitting of the spectral lines is possible, and that is called as Paschen-Back effect too, but that is not given in option. So correct option as per now here is this B, it is called as normal Zeeman effect. Then question number 9, again a theory question. The splitting of spectral lines due to electric field is known as, again it is a Stark effect. It is neither normal Zeeman effect nor anomalous Zeeman effect, or there is no question of the quantum effect at all. Now question number 10, from Lorentz classical treatment the Zeeman shift is given by. Let us go to this question number 10. From Lorentz classical treatment the Zeeman shift is given by, okay, dash dash. We have been given 4 options. The Zeeman shift in Lorentz classical treatment is given by delta nu is equal to E into capital H upon 4 pi m. Okay, now here either you have to know the value of E is 1.6 into 10 raised to minus 19 coulombs, value of m is equal to 9.11 into 10 raised to minus 31 kilograms, and if someone knows this value by directly E by m, this is going to be 1.76 into 10 raised to 11 coulombs per kg. This is the value of standard value of charge to mass ratio of an electron that can be used here. So we have to just divide this number E by m by 4 pi, and therefore this delta nu or Zeeman shift is given by 1.76 into 10 raised to 11 into this capital H divided by this value of 4 pi is 4 into this is 3.14, So this comes to be 1.76 into 10 raised to 11 divided by this approximately comes to be 12 point something. So 4 into 12 is 4 into 4 is 16 plus 1 1 is there, 4 into 1 is 1, so it is for 12.56, and if this number is calculated, so it is 17.60 into 10 raised to 10 divided by this is 12.56. So this approximate calculation gives me 1.40 into 10 raised to 10. So there are 4 options given. First option is A option is 1.40 into 10 raised to 10 value of this h in per centimeter. This is the unit of this shift, so it is per centimeter the unit, it is because of that. B is 1.40 into 10 raised to minus 10, that is incorrect. 1.40 into 10 raised to 11, that index is also not correct, this is incorrect, and this is also not correct. So correct answer of this question number 10 is E, that is 1.40 into 10 raised to 10 hertz, into h per centimeter. So this is all. Question number 10 is numerical question. Now question number 11, Zeeman effect is either magnetic, optical, magneto-optical or electric. So there is no question of this electric phenomenon. This is neither completely optical nor it is completely magnetic. So it is magneto-optical. We are putting this source in magnetic field and thereby its spectrum is being observed, and this spectrum, this particular effect is called as Zeeman effect, and therefore it is magneto-optical phenomenon. So neither optic nor completely magnetic, it is combination of magnetic and optical, therefore it is magneto-optical phenomenon. Now question number 12, when viewed longitudinally, the two lines are found to be dash dash in opposite direction. So there are plane polarized, then there is a circularly polarized. Option C is both plane and circularly polarized, and none of the above. So that is how we might have drawn this diagram earlier. In the normal Zeeman effect, when we go for this transverse view or perpendicular view, we get 3 different lines, and all these lines are plane polarized. Okay, whereas in case of the longitudinal view, we get only 2 lines. This in between line or original line is missing, and these 2 lines they have found to be polarization. They are circularly polarized, and these polarizations are opposite to each other. That means if it is right-handed, then this is left-handed, or if it is right-handed, then this is left-handed. This polarization is shown in the longitudinal view, and therefore the correct option is this circularly polarized. So correct option is C. That is why when 12 when viewed longitudinally, the 2 lines are found to be circularly polarized in the opposite direction. That is to be remember what happens in the perpendicular view, what happens in the longitudinal view. Transverse as well as longitudinal, these views have these orientations of the polarization of the light, and that is shown to be as in the example. Then this Bohr Magnetron has the value. Now see, the Bohr Magnetron is given by, it's very simple expression for this, mu b is given by E into h upon 4 pi m into c. Again here all these numbers are known to you. E is charge of the electron, h is Planck's constant, 4 pi is again a constant, m mass of the electron, and c is the velocity of light. So replacing these numbers, I'll get this to be 1.6 into 10 raised to minus 19. Then this is 6.63 into 10 raised to minus 34 joules second. Okay, that is the unit of this particular h, or that is Planck's constant. This is 4 into now 3.1214 into mass of the electron is 9.11 into 10 raised to minus 31, and c is this is 3 into 10 raised to 8. Now please see the indexes there. So what are the numbers, etc., but can go here, and this is how it is minus 19. So I'll write separately 1.6 into 6.63 divide by all these numbers are 4 into 3, that comes to be 12.56. okay, that product of these two into 9.11 and into this is 10 raised to this is here it is minus 19 plus 34. Taking this here, it becomes plus 31, and this is minus 8. So let's calculate this. Minus 19 plus 34. So here plus 3 is remaining there. plus 3 and minus 8 will be minus 5, and therefore this becomes to be into 10 raised to minus 24, and you'll find this is comes to be 10 raised to minus square, and all this 1.6 into 6.63 into divided by 12.56 into 9.11. If this calculation is done over the calculator, you will get this answer to be 9.27. So 9.27 into 10 raised to minus 24 joules per Tesla. This is the unit of this Bohr Magnetron, and therefore correct option of this question number 13 is A, and this value should be known to everyone. So this is Bohr Magnetron is the minimum unit or the unit of magnetism of an electron in the atomic physics. Now this is another question, is the unit of magnetic moment is, again this is what a very simple and theoretical question. Suppose this is the direction of the magnetic field, okay, this is the direction of the magnetic field, and if I keep some magnet in this particular magnetic field, so this is, it has certain small n pole and this s pole, it has its own magnetic dipole moment. We have to calculate this, and when this particular magnet is kept in the magnetic field, because of this interaction of this external magnetic field and magnetic moment of this magnetic there exists a certain torque which is given by this mu into b bar. So mu bar into b bar, we have to calculate this mu. Torque tau is measured in newtons into meter, okay, so torque is measured in newtons per newtons into meter. Therefore if I use this, it is newtons into meter is equal to mu into b. If I go for the simple calculation, this is b or h, whatever it is, which is measured in Tesla. Therefore this mu will be given by, magnetic moment is given by newtons into meter divided by Tesla, that is the unit for the magnetism. And note that Newton into meter is nothing but this is just like force into displacement, and force into displacement is nothing but work, and therefore this also work is expressed in joules. So unit for work is joule, so I can use that here, and therefore this unit for mu becomes Newton meter, that can be expressed as joules and per Tesla, okay. So this is joules per Tesla is the unit for the magnetic moment too. So magnetic moment is expressed in different number of units. Current, that is I into a square, or ampere into a square. So that is also ampere into area, ampere, that is I into a square, okay, area square. That is also another unit that is used in this particular case of the measurement of the magnetic moment. So though this question is not from the atomic and molecular spectra, doesn't matter, we should know that this magnetic moment has plays a very important role in our discussions, and that's what this answer is, joules per Tesla. So actually of the given options, ergs per Tesla is also possible unit in SI, or this should be joules per Tesla, okay. So that correction you can make, and that's how this is the another unit of this magnetic moment. Now let's come to the question 15. The Zeeman effect gives confirmation of, that is how it gives a confirmation of orbit quantization, spin quantization, space quantization, and simply idea of quantization. So that is gives rise to a confirmation of the space quantization. That is how the because of this magnetic properties of an electron and the magnetism that given to the atom itself, because of this electron orbits in an atom take only certain directions. So very preferred directions are taken, and this particular concept is called as the space quantization. So according to quantum mechanics, all possible orbits are not possible. That means as long as you are not using magnetic field, then the orbits may be random or in any directions for a particular electron in an atom. But when if this particular certain external magnetic field is applied, in that case this magnetic moment or this orbits gets oriented in such a direction that a particular directions will be taken, and that is what called as a quantum principle, and this concept is called as space quantization. So space is quantized, and therefore Zeeman effect has confirmed the concept of space quantization, which you have already used in the vector atom model too. So question number 15, answer is C. Now question 16, Stark observed the splitting of dash dash in the spectrum of the hydrogen. So Lyman series, Balmer series, Paschen series and Brackett series. So naturally answer would be Balmer series because this is in the visible region. Okay, otherwise this is in ultraviolet. We won't be able to see with our own eyes. Then this Paschen and Brackett, these are infrared. Again, that is again not to be visible radiations. So visible radiations, the spectral lines are found to be splitted when this particular source of the radiation is kept in the electric field. That is Stark effect, and therefore naturally the option here, correct option is Balmer series. Since it is in visible region, that lines are observed by Stark. That splitting of such type of optical lines is found, and this is why that is called as the Stark effect, and therefore correct answer of this question number 16 is B. Now this is again a theoretical. Up to the field of 1 lakh volts, okay, 100 million, 100,000 or 1 lakh volt per centimeter, the resolution increases in proportion to the field strength, and this is called as a linear Stark effect. So to a certain range, that particular effect, that means as increasing this voltage, the separation between lines goes on increasing linearly. That means if this is for 10,000, then into the proportion of 10,000 or one, if I go for this 1000 volts, then this is separation. If I go for 10,000 volts, okay, 10,000 volts, then this will increase 10 times of original. This is, if it is 1, this will be 10 times separation. Then if I go for 20,000, this will be 20 times separation of the initial one. This is called as linear Stark effect. Whereas if in some cases, if this particular voltage is increased more than that, then there is no chance, there is no possibility that the splitting of the spectral line will be linear. It may be non-linear, and that type of effect is called as the quadratic. That is what the next question we are going to discuss here. So question number 18, in case of more intense field, more complicated effects called as the quadratic Stark effect. Okay, so this is what the option, that is question number 18, that is C, quadratic Stark effect. Here the separation of the spectral lines doesn't go increasing linearly as we increase this electric field, but it goes on increasing very randomly, abruptly, and that is called as a quadratic Stark effect. Then question number 19, for ground state there is no first order Stark effect in case of, that is what the case of the special element, that is the hydrogen. In case of ground state, this hydrogen atom doesn't spectrum doesn't get splitted at all, or actually energy levels doesn't get splitted at all, and that's why Stark effect is not usually observed in case of hydrogen for this particular in its ground state. So that is what one speciality of the Stark effect that one should remember. Question number 20, the quantum confined Stark effect is widely used for. Okay, this is a quantum confined Stark effect. So when we go for actual, we use this vector atom model, and then we go for study of this Stark effect. That particular thing is called as quantum confined Stark effect, and you will find that this Stark effect is widely useful in the quantum optical communication, optical fiber communication, and in the optical fiber communication, this semiconductor based optical modulators are there. So both these options A and B are correct. So we can construct this type of semiconductor based optical modulators which are used in this optical fiber communication. So both option A and B are the correct options. So question number 20, correct option is both A and B. So the quantum confined Stark effect is widely used for optical fiber communication, which is possible because of this semiconductor based optical modulator. So both of these options are correct, and that is what question number 20 option, correct option is C. Now question number 21, the precessional frequency of electron orbit when placed in the magnetic field 6T. Okay, this is 6 Tesla we have been given, and this precessional frequency is given by a formula which is given by the expression. Already we have seen this expression one times. It is E into Bz, just let me, it is given by EH upon 4 pi m. This is the expression for that, and if I use this particular expressions, so let's go for this. It is 1.6 into 10 raised to minus 19 coulomb. This H is going to be 6 Tesla, divide by this is 4 into 3.14, and if it is multiplied by mass, this comes to be again 9.11 into 10 raised to minus 31. So again go for this. So it is 1.6 into 6 divided by 4 into 3.14 into 9.11, and this is minus 19, this is minus 31. So taking this in the numerator, it becomes 10 raised to plus 31, minus 19 gives you plus 12, and see the denominator is more than the numerator. So adjusting these numbers, I'll get this answer every will be 8.4, and this is 10 raised to, now it will become 10 raised to 10, and that's why the correct option of this particular question number 21 is A, that is 8.4 into 10 raised to 10 hertz. So here in this particular chapter, what you have to go for study at home regarding this MCQs, that what are the actual normal Zeeman effect, what do you mean by this anomalous Zeeman effect, how splitting is observed there, how Zeeman splitting is given, then what is the Stark effect, what is the theoretical application of Stark effect, what are the applications of the Zeeman effect. These are the important things that are to be found important from the multiple choice questions that examination that is to be scheduled in the next month for the SPPU. I hope this video will be again found useful to you all, and in the next video we are going to prepare the video on these X-ray spectra. So till then we will stop here, and thank you for a patience listening. I hope this particular series will be very helpful to you all, and please give your comments as well as suggestions if it is possible in the response to these videos. Thank you.